All right, so now we're looking at the last part of the respiratory system, and this is gas transport. And this one will be a little bit in depth, I believe. So hopefully I will make it clear where you can follow. It is, I know it can be a little confusing, but when you get it, when you kind of see the picture, it makes sense. So obviously in gas transport, we're talking about oxygen and carbon dioxide in our body. And when we look at this, we're gonna look at how the body carries both O2 and CO2 between the lungs and the body cells. As gases enter the body, they dissolve in the plasma and or chemically combine with the other substances. So we first look at oxygen transport. Almost all of the oxygen is going to be bound to hemoglobin. A small percentage, less than 2%, is going to be just dissolved as a gas in the plasma. And so this, the hemoglobin, is the main one we're going to look at. First, you should know that oxygen is going to bind with iron. Fe is iron. It binds with the iron that's in the heme portion of the hemoglobin. And for each one hemoglobin molecule, 4 oxygens can bind to it. And so the chemical bonds between oxygen and hemoglobin are pretty unstable, and their stability is going to be determined by their environment. And so we're going to look at the things that increase the release of oxygen from hemoglobin. So again, oxygen is going to bind to that iron. There's 4 oxygens bound to each hemoglobin molecule. And as it travels from the lungs to the tissues, it's going to go through a bunch of different environments as it's looking at. And so what will happen is when the oxygen, the partial pressure of oxygen decreases, hemoglobin is going to want to let go of oxygen. When the partial pressure of carbon dioxide increases, hemoglobin is going to want to let go of oxygen. An increased acidity, or said another way, make sure you understand this, a decrease in pH. All right, so if I go from 7.4 to 7.35, I've decreased pH. So a decreased pH or an increase in acidity makes hemoglobin want to let go of oxygen. And finally, an increase in temperature makes hemoglobin want to let go of oxygen. Now, I want to just stop and have you think about this. When an exercise is the best example, or doing some kind of exerting yourself. If I exercise, if I go to the gym, get on the treadmill, one of the first things you're going to notice is it'll feel like the temperature in the room increased. Because as you use your muscles, over half of that energy that's released in making ATP is released as temperature, as heat. And so as I start exercising, my temperature is going to increase. Hey, when I exercise, I need to increase my oxygen to the area. So isn't it pretty nice that as I exercise, the byproduct of exercise, which is temperature, is going to cause oxygen to be released from hemoglobin? Now, as I'm exercising, when I'm starting to burn up the oxygens that's there, I'm going to decrease the partial pressure of oxygen. Then what do you know? So if I am exercising, a byproduct of cellular metabolism, the burning of the oxygen, is going to cause more O2 to be released. Also, when I'm exercising, as I'm breaking down that glucose into ATP, I'm going to, one of the byproducts is carbon dioxide. So I'm going to increase carbon dioxide when I'm active. And what do you know? It causes an increase in the release of O2. As I'm exercising and I'm burning my oxygen, releasing more carbon dioxide, raising the temperature, I'm also starting to produce more hydrogen ions and acids. Again, lactic acid. Right? So if I exercise too much, I increase the acidity or lower the pH of my muscle cells. And what do you know? That also causes a release in oxygen. So the four big factors that cause oxygen to be released are all completely tied with cellular respiration and metabolism. And so I think that that's a pretty cool thing, and it's easy to remember if you can tie those together. The more I exercise, the more I need more oxygen, so the more oxygen is released, because all four things that are part of me burning more energy is going to cause more oxygen to be released. So released oxygen moves from the blood into the tissues. About 75% of the oxygen remains bound to hemoglobin in venous blood. So when it's just normal, like you're just sitting there watching these videos, you got the heart, and I'm going to draw the tissues. I'll draw the body here. Under normal conditions, as the heart comes around, it's going to have, hopefully 4 oxygen for each hemoglobin. That's referred to as saturated. Once it gets in the venous system and it comes back to the heart, I'm still going to have 3 oxygen attached to it on average. This is why now they've gone from having to do, when you're doing CPR, you no longer have to provide as many breaths. You just have to keep the heart beating. Because if I can continue getting the blood flow, I still have enough oxygen in the blood to remain stable for a little while. Now, if this guy right here starts exercising or doing something active, it's going to take more of those off, and instead of 3, maybe it'll cause it to release 2 oxygen, and as it comes back, and so I only have 2 left when it comes back. So this, if there's 3, this is 75% saturated. If there's 2, it's 50% saturated. And let's say you're really exercising and you only have 1, that is 25% saturated. So the way this works is it's a very well-run system. The body has more than enough oxygen as it's going through. It only releases a quarter of it under normal circumstances, but that makes sure that I have 3/4 of oxygen in reserve if I need it and I need to tap into it. Now we're going to go through a couple of these charts. I'm not going to tell you to memorize anything about these charts. I'm just hoping they help you see certain things. All this is a chart between the partial pressure of oxygen and the saturation on hemoglobin. So the higher the partial pressure of the oxygen, the more saturated the hemoglobin is going to be. So if I get down and I've got a partial pressure of 100, so remember we were looking at the heart, it said, or in the VLI, the gas exchange, it was about 100, a little over 100. So at 100, we're going to have 100% saturation. Now, again, as we go through, the saturation levels change. We have 75% saturation levels under normal conditions. That generally is going to be about 40. Having a partial pressure of 40. Again, not really concerned about much of this, as just wanting to know the basics of what's going on. This is talking about the schematic of what's happening. So the VLR partial pressure of oxygen is 104. We said that as the blood is coming back, it's 40, so it's going to come through here. As it goes through, I'm going to have the oxygen jump across because of the pressure gradient. This will be saturated. It's going to come through, and if you could see, here there's only 3 oxygen on this molecule. On this one over on this side, you can see that there's 4. As it goes down, it's going to come through the capillary bed, and in the capillary bed, it's going to be in the middle of an environment that has low partial pressure of oxygen. That's going to cause oxygen to want to come across. Low partial pressure of oxygen causes it to be released from hemoglobin. I'm going to have an increased level of CO2 in this area, and that's going to cause oxygen to be released as well. I'm going to have a temperature that's greater here. That's going to cause oxygen to be released. And there's going to be an acidic environment that causes oxygen to be released. So that's how it's transported through the blood. And just remember, hemoglobin is 75% saturated when it's in the venous system. So that's talking about after it's gone through the capillaries, and on this side, it's still 75% saturated. These kind of show the saturation curves again. I'm not going to have these on the test. I'm not worried about them, but there's just showing you that as the for this, the partial pressure of carbon dioxide increases, I have a lower saturation level. That means that more oxygen's been released. Same thing here on the pH. As the pH gets lower, or I should say becomes more acidic, I'm going to have a lower saturation level of the hemoglobin because more oxygen is going to be released. This is the same for temperature. Now, carbon dioxide, this down here at the bottom is that equation. We've looked at this before. We're really going to hit it again here. So carbon dioxide transport, carbon dioxide is much different than oxygen. It has three ways, and they're all used. There's a larger than normal percentage that's dissolved in plasma. It's going to be bound to hemoglobin as well. And the largest part is it's going to be used as part of this bicarbonate ion buffer system. All right, that's the majority is transported as bicarbonate. And we're going to talk about all three of them, but remember, this is what we were referring to when carbon dioxide it acts as an acid in our body. If the carbon dioxide levels rise, this equation gets pushed this way, and so when carbon dioxide levels rise, so do hydrogen ion levels. And so when hydrogen ion levels increase, that means acidity increases, or said another way, pH decreases. All right, so this is a buffer system in our body that's meant to try and keep pH normal. Because if I have extra hydrogen ions, this bicarbonate, which is the way that it's transported, is going to absorb that and form carbonic acid, which is going to break down to water and carbon dioxide, and then we breathe out the carbon dioxide. So this is how it works. Now, when we're looking at it, this is the schematic of it. It's showing the three different ways. There's a small amount that gets dissolved into plasma. Some of it will go in. The CO2 is going to combine with hemoglobin, forming carboxyaminohemoglobin. Now, not a big deal, but this, we looked just a minute ago and said that as the partial pressure of carbon dioxide increases, the ability for hemoglobin to hold on to oxygen decreases. And that's because carbon dioxide actually comes into that molecule and kicks oxygen out. Imagine being, driving down the street in a taxi and you're an oxygen molecule. You're going to get to a certain point, and if there's a lot of other people grabbing for the taxi, CO2 basically reaches in, grabs an oxygen, pulls it out of the taxi seat, and then sits down. So some of it's going to bind to hemoglobin, but the majority of it goes through this, which we said is the carbonic acid bicarbonate cycle. It's going to be dissolved into the cell. It's going to bind with water. There's going to be an enzyme in there that makes this happen, forming carbonic acid, which will then break down into hydrogen ions and bicarbonate ions. All right, so the hydrogen will then bind to hemoglobin, which also, just like I was just saying with the carbon, is going to go in and kick out an oxygen. So the more hydrogen ions I have, again, means it's decreased pH or increased acidity is going to go in and pull more oxygen off of the hemoglobin. Again, same thing that we had just talked about. Then we look at once this bicarbonate is formed, it's going to be pulled out, and we're going to see something that happens with it in just a minute, and it's going to flow into plasma. Now, once it's in the plasma, this acts all throughout the body as a buffer. It's going to be a huge part of our body's ability to regulate pH. And so that's what's going to start there. And that's a terrible word. Looks like butter almost. Anyway, I'm so sorry about that. But that's what's happening. I hope that makes sense. I'm trying to kind of make light of some of this stuff because I know it's kind of dry. But it's really amazing. I mean, when you think about what all goes on, And the complicated process of this and all the checks and balances to make sure it's going to function right, it is an amazing system that's there. All right, so those are the three methods of O2 transport in the blood. Bicarbonate ions is the main one. The thing about bicarbonate ions, because it is an ion, all right, it is an electrically charged molecule. If we were to have that leave the cell to get in the plasma like it does in order to be used, if I had a bunch of that left, I would destroy the cell because I would change the polarity of it. I change the charge of it. So what happens is for every one bicarbonate ion that gets pushed out, a chloride gets pulled in, and this is called the chloride shift. And so the chloride is going to hang around the red blood cell, and in the tissues, it's going to be pulled into the cell in order to let the bicarbonate leave. Now, when this cell gets close to the lungs, what's going to happen is it's going to reverse. Chloride is going to push itself out, and when it does that, that's going to cause this to reverse and bicarbonate to be pulled in. And when bicarbonate gets pulled in, it breaks down, produces water and carbon dioxide, and we breathe out the carbon dioxide, which you can see in the next picture. All right, this is what's happening once this is in. Now it's in the alveoli, it's in the lungs. And so it's going through, and once it gets here, again, we're going to have the little chloride shift. The chloride leaves. The bicarbonate gets pulled in. It's going to break down into hydrogen ions, or it's going to combine with hydrogen ions, and that's going to form carbonic acid, which will break down into water and carbon dioxide. Now, when we breathe, these are the two main things we breathe out. Remember, I don't know if you know this, I shouldn't say remember, but a long time ago, if someone had passed out and you didn't know whether they were alive or dead, you would put a mirror under their nose to look for condensation. We breathe out a lot of this water. We actually lose over a 12-ounce can of water every day just simply from breathing. But that's part of this process. So again, hydrogen ions will bind with bicarbonate to form carbonic acid. That breaks down to carbon dioxide and water, and we breathe these out. All right, so that's the process of gas exchange. And so that's how oxygen is transported, and that's how carbon dioxide is transported. This gives a pretty good breakdown of each. Again, I'm not worried about I want you to know that a small portion of oxygen is bound in the plasma, but the majority of it is bound to hemoglobin. Carbon dioxide, less than 10% dissolved in the plasma. It's still greater than what the oxygen is, but about 7% is dissolved in the plasma. This is what those chemoreceptors are monitoring. And then about 23%, a little under a quarter, is going to bind to the hemoglobin. All right, this is going to help kick out the oxygen. And 70%, close to 70%, is going to react with water to form carbonic acid. The carbonic acid breaks down and releases hydrogen ions and bicarbonate ions. And then the bicarbonate ions are going to be used throughout the rest of the body as they're making the journey back to the lungs to help keep pH balanced. And that's the respiratory system.